Right, thank you. I'll try and make this as quick as possible because I realise we're running quite late in the day and there's not going to be much time for conversation. So my presentation neatly follows on from what Michael Osling's has been talking about, so it saves me a long introduction. A sustainable future needs to be more electric, and I think many people would agree with that. We need to move away from fossil fuels and all the rest of it. And energy generation is great, and you can use wind power, sun power, water power, and so on in order to achieve that end. There's a range of applications. One of the areas that we're interested in at Newcastle, we have a doctoral training centre looking at electric propulsion. So we need to convert what comes through things like wind power and water power and everything else to use in things like more electric aircraft, more electric cars, as well as all of the IT products that we all know and love, and data centres, all of which consume vast amounts of energy. And the big problem, as Michael has pointed out, one of the big problems is energy conversion. It would be great to have 100% efficiency between the energy generated and the energy being used, but that's just not the case. And just thinking about the voltage range that you need for different applications, the voltage range you need for a smartphone is very different to what you're going to need for an airplane. So there's a lot of work just in terms of energy conversion, and within that even DC to DC, DC to AC conversion. That's done largely by silicon at the moment, and the pitch that Michael gave was one which I would of course endorse in this presentation, which is wide bandgap semiconductors have got some great properties. I'm focusing mine on silicon carbide, but I've got gallium nitride in my slide just here. If you just look at the basic properties here, the blue is silicon, the orangey color is silicon carbide, and the gray one is gallium nitride, so I'm less interested in that. You'll notice that silicon carbide's got brilliant thermal conductivity, much better breakdown electric field compared with silicon. Energy band gap, again, a lot bigger, so that's why it's the wide band gap. And then these are the transport properties. Electron mobility is not quite so good, but velocity saturation is higher, so it depends what you want to pick there. The consequence of that is that you get higher voltage operation for silicon carbide, and I think, as Michael said, you tend to see power electronics splitting between gallium nitride at the lower voltages and silicon carbide at the higher voltages. And you can get a wider temperature range because it's not only a high electric field as a result of the wide band gap, but it means that you can operate to higher temperatures because you haven't got the problem of intrinsic carrier concentration getting too high, for example. So you get a whole load of efficiency gains that way. This is just a timeline of electronic devices in silicon carbide. I started working on it about 20 odd years ago, and then stopped working on it for quite a bit, and then started working on it again about 5 years ago. And it was intriguing to me that one of the big problems, and one of the things you will notice from this slide, if you can squint at it, is that there's an awful lot of devices here, but they tend to be ones which aren't MOSFETs. There's JFETs, there's normal FETs, there's bipolar transistors, and they have their place and they're useful, but MOSFETs tend to be the workhorse technology. And you can make those brilliantly in silicon, and it's really why silicon has been so successful. So that remains and has remained a problem in silicon carbide. As I say, back at around 2000, when I first started looking at this, the big problem was very poor mobility as an MOS interface, and I came back to it in 2015, 2016, and that was still a major problem. Compared with silicon, where you have electron mobilities in the region of a few hundred centimeters squared per volt second, in silicon carbide, those mobilities are down at around about 1 to 10 centimeters squared per volt second, so really quite poor. So that was an area that we wanted to work on. The whole thing is complicated by the fact that silicon is just so peculiar. There isn't a liquid state of, or convenient liquid state of silicon carbide. And when you try to make it, although it's got a nice tetrahedral bonding in the way that you would expect of silicon, you get a whole range of different polytypes. There's around about 50 or more polytypes. So it's very difficult to get single crystal material. And then within those, you've got different electronic properties. The one that we tend to focus on is 4H silicon carbide. So the interest for me and for the people working with me at Newcastle has been on MOSFETs. I've worked on MOSFETs with strained silicon and things like that for a lot of years, and then tried to apply that to silicon carbide. So just to remind you of the structure, you've got a source, a drain, and a gate, and you've got N-type doping underneath the source and the drain. A P-type substrate, you apply voltage to the gate, which will be positive, that attracts electrons to create an inversion layer at this silicon dioxide semiconductor interface. As you increase the gate voltage, then you get an increase in the drain current, and that follows this kind of exponential behavior in gate voltage and then gradually rolls over. So the drain current can be conveniently described as being proportional to an exponential of the gate voltage multiplied by E over KT and some fiddle factor n, which takes into account things like defects in the material and defects particularly in the interface, which are going to affect the current. Ideally, if that value n was equal to 1, then you can put the numbers into that and realize that at room temperature, the subthreshold slope should be about 60 millivolts per decade. And so that's what the gradient of this slope should be. And then you've got the ID/VD characteristic up there. So that's background, I guess, for most of you, but hopefully to refresh your minds. So this is what I considered to be the problem when we came back to look at this. When you grow an oxide on silicon carbide, it's great that you get silicon dioxide, and it's one of the few semiconductors that has a natural oxide that stays where it's put. It doesn't dissolve in water or anything, it's silicon dioxide. However, it's just silicon dioxide. The carbon isn't or shouldn't be in it, and some of that carbon can get away in gaseous form, carbon monoxide, carbon dioxide, but some of it is going to remain, and the more oxidation, the more carbon is going to be there. And so if you are to look at the defects at this interface, they're pretty enormous compared with what you would find in something like silicon because of these carbon related defects, for example. So this is a plot of the density of interface traps at that interface as you go through from the valence band to the conduction band. And you can see the numbers up here are up at around 10 to the 13, 10 to the 14, which is really just too bad. And that's why I expect you get the very poor mobilities. So having worked on silicon for a lot of years, I reasoned that perhaps an alternative would be, well, you just don't go quite as much oxide. If you think of, I think it was the 45 nanometer CMOS technology, what people did was move to a high K dielectric for different reasons. But even when they'd gone to high K dielectric, they had to go thin oxide just to make sure that the thing worked properly, to get the defects sorted out by this thin oxide. So what we chose to do instead was to go a very thin oxide, create fewer defects. It allowed us to use a deposited dielectric in order to get the appropriate effective oxide thickness. And lo and behold, when we look at the density of interface traps, that came down by about 2 orders of magnitude. So that puts us in a position where we expect, therefore, the MOSFETs to be a lot better. This is just looking at a capacitor structure. So this is some of the work that we published a couple of years ago, looking at the high mobility enhancement mode MOSFETs using this thin silicon dioxide. So this is the idea. So you grow a very thin oxide just here and then deposit the dielectric on top. Because it's a thin oxide, you don't get as many defects. And when you look at the IV characteristics, the solid black line, this is a plot of drain current vertically and gate voltage horizontally. You can see you're getting a really good IV characteristic with the thin oxide approach compared with the control thick oxide approach. So for example, the subthreshold slope, although it's not 60, it's about 120, which is still pretty good compared with about 500 as a subthreshold slope, millivolts per decade, for the thick oxide approach. So although there are silicon carbide MOSFETs in production, the gate stack is still compromised and needs work to improve it to get it to the state that it could really go on to do everything, including things like CMOS. These are our mobility data. The silicon carbide community used field effect mobility, and that was getting up to about 150. Remember, it was down at about 10 before. And when we compare it with the effective mobility, which is a parameter you would use in silicon, we're getting it peaking at about 250 centimeters squared per volt second. So these are really significant increases, which is why we're getting this improvement in the IV data. And when we look at this, we can confirm where that's coming from. This is a plot of mobility as a function of temperature, which when the PhD student who measured this saw it, he came back and was really distraught because he couldn't understand. We were expecting the mobility to be higher, and the thin oxide data clearly is higher, but as temperature increases, it goes down. Whereas with the conventional poorer mobility, it increases with temperature. And the reason for that is that they're indicative signatures of what's causing the scattering and therefore reducing the mobility. Down here with the thick oxide, we've got Coulombic scattering because you're getting scattering off the carbon defects. And as the temperature increases, your electrons are spending less time in the vicinity of a carbon defect, so the mobility goes up in a hand wavy sort of way. What we're finding up here with our thin oxide data is that we're getting a reduction, a negative temperature gradient corresponding to phonon scattering because we got rid of the Coulomb scattering. And if you think of phonon scattering, then you can imagine as the temperature goes up, you're getting more lattice vibration and therefore more mobility degradation as a result of that. And then this final plot is a universal mobility curve, which is much loved by people in the silicon electronics community to try and see how, things like strain silicon that we worked on, that allowed us to move beyond the normal universal mobility. So this is a plot of mobility against effective field, which effectively is gate voltage. And you have different contributions to mobility in any material system. So you have Coulombic scattering, you have phonon scattering, which is very material dependent, and surface scattering, which is something which is particularly important at higher gate voltages. This is the silicon data, and depending on, it doesn't really matter what silicon transistor you've got, you tend to get this universal response to gate voltage. What we found is, in the case of our silicon carbide devices, we're now getting within about 50% of what you can get in silicon. So that's a big, big improvement on the data that you would normally get with the thick oxides, which would be down at the bottom of this graph somewhere. So we were really quite pleased with the fact that we're starting to get something now which is looking like a proper MOSFET technology. And we've been continuing to make progress on that, and we're hoping to get some stuff out in print before too long. So that's just a quick conclusion, hopefully a relatively quick talk. I think silicon carbide electronic device technology is going to be really important for electric future, a more electric future. The energy conversion is a particular thing, but also just the fact that at high temperatures, you could probably use this kind of technology in situations where you don't quite need the same level of cooling that you would do with silicon technology. And we've just demonstrated these thin oxide devices as hopefully a way forward for MOSFETs in silicon carbide. But there's plenty more stuff to do. Okay.